Welcome, curious minds, to another deep dive. In our increasingly digital world, information isn't just power, it's really the lifeblood of our daily existence.
It absolutely is.
I mean, from streaming your favorite show to managing global financial transactions, we live in this on-command, on-demand era, don't we? Immediate, uninterrupted access to information is just, well, it's non-negotiable.
Absolutely.
Hmm.
And the sheer volume, the incredible velocity of data we create and consume every single day,
Mhm.
it means ensuring its constant availability, its unwavering integrity. It's a monumental task,
Hmm.
but it's absolutely critical.
Yeah,
It's about so much more than just, sticking data somewhere. It's about building resilience into every system, guaranteeing speed when you need that info back,
Mhm.
and embedding intelligence into how it's all managed. Think
Right.
about it. A financial trade that can't complete, or a critical patient record that's suddenly inaccessible. Those aren't just minor bumps, they're potential catastrophes.
Absolutely, and that's exactly what we're unpacking today. We're taking a deep dive into the fascinating world of local replication. Think of it as the meticulous art and, well, the precise science of creating exact copies of your data, right where it lives, basically, to ensure it's always there exactly when you need it.
Yeah, the invisible engineering.
Exactly. It's the invisible engineering that keeps your systems humming along smoothly without missing a beat, even when, things go wrong.
Our mission today really is to equip you with a clearer understanding of how these invisible but utterly vital processes keep our digital world operational, resilient, and performing optimally.
Okay.
We'll explore the foundational principles, dive into the ingenious technologies that make it all happen, and then zoom in on how these concepts specifically apply to those virtualized environments that power so much of modern computing.
Right, the VMs.
Exactly. So let's unpack this crucial topic and find out why it's more important than ever for every organization, large or small. The foundation. What is local replication and why we need it?
Okay, so to kick things off, let's get on the same page. When we talk about replication in the data world, what does that actually mean? And why the specific focus on local replication? What's the core difference?
Sure. So at its core, replication is simply the process of creating additional identical copies of your production data. It's like making a perfect duplicate of your most important files.
Okay, simple enough.
Now, the local part, that's where the immediate benefit comes in for today's chat. Local replication means the data is copied within the same storage array or within the same data center, so it stays incredibly close to the original.
Right next door, basically.
Exactly. Right next door, which is absolutely key for immediate availability and, crucially, lightning fast recovery. Think of it as having an identical twin of your data ready to jump in at a moment's notice.
So it's not about sending data miles away then. That sounds like a different beast entirely, maybe for bigger disasters.
Precisely. You've hit on an important distinction just for context. There's also remote replication, where data gets copied to a geographically distant site.
Right.
That's usually for disaster recovery, against large-scale regional outages, floods, massive power failures, that sort of thing.
Gotcha.
But for today, we're concentrating on those copies that stay right at home, close to the action, for that everyday resilience and operational agility. The main point of local replication isn't just making copies for fun. It's about strategically duplicating data to achieve really critical business goals.
Like what specifically?
Things like ensuring constant availability for your customers, boosting the performance of your applications, and, crucially, enabling lightning-fast recoverability from common issues. It's about building a robust safety net right where you need it most.
Okay, so beyond just having a spare copy, what are the really compelling reasons businesses invest so much in local replication? What specific problems does it solve that make it, well, non-negotiable today?
It solves quite a few, actually, and often in ways that really change how a business can operate. Think about the challenge of managing tons of live data while also trying to protect it without messing up operations.
Yeah, that sounds tricky.
Local replicas become indispensable tools. They allow for continuous business operation where before you might have faced slowdowns or even downtime. One of the biggest uses is as an alternative source for backup.
Okay, how does that work?
Well, the classic problem with traditional backups is they often involve reading data directly from production volumes, those LUNs where your live business stuff is happening.
Right, while people are actually using it.
Exactly. When you're trying to handle live customer transactions, run complex queries, and back up that same data simultaneously, it creates a significant additional burden on the production system.
I can see that. Slowdowns.
Yeah, slowdowns, hits to application performance, and it extends those dreaded backup windows, the time during which your systems might be impacted or even have to be paused.
Ugh, yeah. I can imagine that being a huge issue for, say, an e-commerce site during a big sale or a trading platform. You can't just pause everything.
Exactly. And that's where the local replica solution really shines. It's a game changer for businesses needing continuous operation. Because a local replica is an exact point in time, PIT, copy of the source data.
Like a perfect snapshot.
Precisely. It can be used as the sole source for backup operations. This completely offloads the heavy lifting of the backup from the live production system.
Ah, that makes sense.
The impact is immense. It alleviates the production I/O workload, allowing your critical apps, that e-commerce site, a factory control system, to continue unimpeded. This leads to a critical benefit often called a zero backup window.
Zero backup window.
Yeah. You can back up even a global e-commerce site during peak sales without a hitch because the backup runs against the replica and not the live system. It enables true 2,147 operations.
That's a massive leap. But beyond scheduled backups, what about getting back online fast if something actually goes wrong? Like someone deletes something important or a software update messes things up.
Right, that brings us to fast recovery. And unfortunately, that happens more often than you'd think. Imagine data loss or logical corruption on your primary production system.
Oops.
Yeah, could be human error, someone drops a table, or a software bug, maybe even malware. Local replicas provide an immediate local copy to restore data from.
Faster than capes, I assume.
Much faster. Compared to, say, restoring from offsite tapes or even a remote cloud backup, this means much faster recovery times. For businesses, this is absolutely critical for meeting tight recovery time objectives, or RTOs.
RTOs, that's how much downtime you can tolerate.
Exactly. If your RTO is, say, 15 minutes, restoring from tape just isn't going to cut it. Local replication means you can recover quickly, minimizing the damage.
Makes sense. What else are these replicas good for?
Well, beyond recovery, they're fantastic for enabling decision support. Lots of organizations today need to run complex analytical queries, generate huge reports, do data mining.
The heavy lifting analysis stuff.
Right. And that stuff is incredibly I/O intensive. It can severely impact the performance of live applications if you run it on the production system.
So you use the replica.
Exactly. Create a local replica, run those decision support tasks directly against it. This lets the business gain insights from their current data without compromising the performance of mission-critical systems. Imagine running quarterly sales reports without slowing down customer transactions.
It's like having a dedicated lab for your data analysis.
Precisely. And speaking of labs, local replicas also provide an excellent testing platform.
For trying out new things.
Yeah, implementing new applications, applying patches, making big configuration changes. Doing that on a live system is inherently risky.
Do you hope it works?
Right. A local replica offers a perfect, up-to-date, isolated copy of the production environment for thorough testing. You can validate extensively, minimize the risk of introducing errors or downtime into the live system. You can, break the replica all you want.
Without consequence.
Exactly. Without affecting production. It's invaluable for stability. And finally, maybe a bit more niche, but they help in facilitating data migration. They can act as an intermediary step for moving data between systems with minimal disruption.
Okay, so these replicas are vital tools, but you said they need to be good copies. It's not just any copy, right? There must be rules.
Precisely. You've hit on a crucial point. A replica isn't useful unless it meets certain criteria. 3 characteristics are absolutely paramount.
Okay, what are they?
First is recoverability. This just means the replica must let you restore data from the replica back to the original source if the source gets lost or corrupted. It's the ability to reverse the flow, basically.
Got it. Bring the original back to life.
Second, restartability. This is key. It means you can actually start or resume business operations directly using the replica if your primary system fails.
So not just restore, but actually run on the replica.
Exactly. It's a functional fallback you can switch over to immediately. Crucial for those really low RTOs.
And the third, I'm guessing this is the big one.
Absolutely. It's the bedrock. The third, and arguably the most critical requirement, is consistency.
Consistency.
A replica is utterly useless, maybe even dangerous, if it's not consistent with the source at the exact moment it was created. Consistency ensures the replica is usable for both recovery and restart. It's the primary goal of all replication tech. Without it, you might restore or restart to a state where the data is corrupted or just doesn't make sense to the application.
How do you guarantee that consistency? It sounds tricky, especially with data changing all the time.
It is tricky. And to understand why it's so critical, we need to quickly touch on something called the dependent right I/O principle.
Okay.
Many complex applications, especially databases, operate on this principle. It means that for a single transaction to be valid, there is a specific sequence of write operations that must happen in a particular order.
Like steps 1, 2, 3.
Exactly. For instance, a database might write a change to a transaction log before it writes the actual data to the main data file. A specific write, like updating data, won't be issued until a prior related write, like writing to that log, has successfully completed.
Ah, okay. So it's like ensuring all the steps in a recipe are followed in the right order. If you copy the steps out of order, the dish won't work.
That's a great analogy. Think of a meticulous accounting ledger. You wouldn't record a new transaction in the main ledger until you first logged all the details, date, time, etc., in a separate journal. If you only copied the main ledger entry but missed the journal entry that came first.
Your replica ledger would be incomplete, maybe misleading.
Exactly. Potentially unusable. For databases, this is fundamental. They require this series of writes in a particular order across maybe different devices or files for a transaction to be valid. Any replication solution must preserve this exact order.
To ensure that transactional integrity on the replica.
Precisely. If the order is broken, the replica might be crash consistent. It looks like the system just crashed at that moment, maybe some files open, some transactions incomplete.
Okay, messy, but maybe recoverable.
Maybe, but it won't be application consistent. That means the application itself won't be able to restart or recover cleanly. It would likely fail or throw errors because its internal data structures are out of sync.
So crash consistent is like finding your house after an earthquake structure's there, but everything inside is a mess. Application consistent means everything's tidy, ready to use.
Perfect analogy. Application consistent is what you always aim for. And one last point on replica types. They can be point in time, PIT, or continuous.
PIT versus continuous.
Yeah. A PIT replica captures data exactly as it was at one specific moment, like a photograph. A continuous replica is constantly or near constantly updated, usually via streaming changes, more like a live video feed. This distinction leads us into the different technologies. 2. The how-to, exploring local replication technologies.
Okay, so we know why local replication is so vital, and what makes a good, usable replica consistency is king. Now, let's get into the fascinating nitty-gritty. How is this actually done? What are the main technological approaches?
Great question. We primarily categorize local replication based on where the brains of the operation live, where the control resides. It can be at the server level, the storage array level, or even within the network itself. Let's start with host-based replication.
So the server doing the work.
Right. In host-based replication, the server itself, typically through its operating system or maybe some specialized software running on it, manages creating and maintaining the replicas. The server's CPU and memory are doing the heavy lifting.
And how does that work on the server? I've heard of LVM, the Logical Volume Manager. Does that play a role?
Yes, a very common method is LVM-based replication using the Logical Volume Manager. LVM is software on the host that kind of abstracts the physical storage, presenting it as logical volumes to apps. It's responsible for creating and controlling the host-level logical volumes.
Right, it manages the disks.
Yeah, quick refresher. You have physical volumes, PVs, your actual disks, grouped into volume groups, VGs, and then within VGs, you create logical volumes, LVs, which look like standard partitions to the OS.
Okay, so how does LVM replicate?
Through something called LVM mirroring. Here, each logical block in a logical volume is mapped to 2 physical blocks on 2 different physical volumes.
So every piece of data gets written twice, simultaneously.
Exactly. When an application writes to the logical volume, the LVM driver makes sure that write goes to both underlying physical volumes, creates a real-time, identical copy right there at the host level.
That sounds like instant redundancy. If one disk fails, the other just keeps going.
Precisely. It's built for high availability for that LV. And the really clever part is that these mirrors can be split.
Split, meaning?
Meaning the 2 physical volumes can be separated to become independent copies. This lets the replicated data be independently accessed for other things, like backups or testing, without impacting the original production volume.
Ah, like your analogy of the 2 notebooks. Write in both, then tear one out for another use.
Exactly that. Very flexible. Now, another crucial host-based tech, and one you've likely used without realizing it, is the file system FS Snapshot.
Oh yeah, I've seen snapshot options. How does that work? It seems quicker.
It is quicker and very different from full mirroring. An FS snapshot is a pointer-based replica. It doesn't immediately copy all the data. Instead, it's incredibly space efficient, usually needing a fraction of the space used by the production FS.
Okay, pointer-based, so it's not a full copy, but like a reference.
Mhm.
How does it actually capture the data then? This copy on first write thing sounds interesting.
It really is clever. It's the core mechanism. When you initiate a snapshot, two key metadata structures get created within the snapshot's file system: a bitmap and a block map.
Bitmap and block map.
The bitmap is basically a map that keeps track of blocks that are changed on the production FS after the snap creation. Think of it like flipping a switch for each block that gets modified. 0 means unchanged, 1 means changed. The block map stores the exact address from which the data is to be read when the data is accessed from the snap FS. It tells the snapshot where to find the original data, essentially.
So immediately after creating the snapshot, where does it read from?
Good question. Initially, all read requests from the snapshot are actually served by reading the production FS. It just points to the live data.
Makes sense.
Now here comes the copy on first write KFW event. If an application tries to write new data to a block on the production file system for the very first time since the snapshot was taken.
It doesn't just overwrite.
No, it pauses that write momentarily. It holds the I/O. First, the original data that was in that production block is moved to the SnapFS, copied to a dedicated area for the snapshot.
Preserving the old version for the snapshot.
Exactly, preserving that point-in-time state. Then, the write is allowed to the production FS for the new data.
Okay, then the live data gets updated.
Right, and immediately after, the bitmap and block map are updated accordingly to show that this block has now changed on production, and its original version is safe in the snapshot area. Importantly, subsequent writes to the same location will not initiate the COFFW activity because the original version is already preserved.
So it only copies the original data the very first time it's about to be overwritten. That's why it's space efficient.
Precisely. It only copies what absolutely needs to be preserved. It's fundamental to how snapshots work and why they're so fast to create.
So how does reading from the snapshot work after some writes have happened?
When you read from the snapshot, the bitmap is consulted. If the bit for a block is 0, meaning production hasn't changed.
Read from production.
Right, the read is directed to the production FS. But if the bit is 1, meaning production has changed, COFW happen.
Read from the snapshot's special area.
Exactly. Then the block address is obtained from the block map, and the data is read from that address on the SnapFS. Meanwhile, reads from the production system just access the live data as normal.
That's incredibly efficient. Seems perfect for quick recovery from, say, deleting a file by mistake. Are there any, common issues with this?
That's a good point. The main thing is performance of that save location or delta area. If it's slow or runs out of space, the CUFW itself can slow down production rates. Also, keeping snapshots for too long with lots of changes can make the snapshot large and sometimes slow to delete. Needs good management.
Okay, so that's the server handling replication. But what if we want to offload that work? If the server isn't doing the heavy lifting, the storage array itself must be. How do those intelligent arrays manage replication internally?
That's right. We moved to storage array-based replication. Here, the storage array itself, with its specialized controllers and software, handles the replication. This totally offloads the host, freeing up its resources. For large environments, this is often a big advantage.
Makes sense. The array is built for data operations. What are the methods?
One is full volume mirroring. Conceptually, very similar to LVM mirroring, but all managed by the array. The source volume is mirrored to a target volume.
Full copy again.
Yep. After an initial synchronization, a full copy, all writes must be committed to both the source and the target simultaneously. Real-time identical copies. And just like LVM, the mirrored care can be split to create an independent point-in-time copy.
But it needs double the storage, right? 100% overhead.
Correct. It requires 100% additional capacity. But once split, there's no impact on the source I/O response because the replica is separate. Good for backup or testing. Robust, but resource heavy.
Okay. Any more efficient array methods?
Yes. A more nuanced approach is pointer-based full volume replication, sometimes called copy on first access or COFA.
COFA. Copy on first access. How's that different?
Here, data is only copied from source to target when it's first accessed after the replication session starts. No big initial sync.
Okay, so how does that work?
If a write comes to a specific address on the source for the first time after starting, the original data at that address is copied to the target, then the new data is updated on the source. This ensures the target holds the data state at activation for that block.
What if you write to the target first, like for testing?
Good question. If a write comes to the target for the first time, the original data is copied from the source to the target, and then the new data is updated on the target. Preserves the target's PIT view before modification. Even for a read to the target for the first time, the original data is copied from source to target first.
So it copies just before any first access read or write, source or target.
Pretty much. And in all these first access cases, a protection bit for that block on the source is flipped, indicating the original has been copied. Subsequent writes to the same block don't trigger another copy.
So the target becomes an independent PIT copy.
Yeah.
But does it still need 100% capacity eventually?
Yes, that's the catch. Despite the cleverness, it still requires 100% capacity, ultimately, because it needs to hold a full copy. It just builds that copy over time as data is accessed.
Okay, so COFA is clever, but still needs the full space. Is there an array-based solution that's truly space-efficient using pointers, like the FS snapshot?
There is, and it's very common now. This is pointer-based virtual replication, often called copy on first write to a save location.
Copy on first write, but to a save location.
Exactly. It offers excellent space efficiency by using a specific dedicated area within the array for changed data, sometimes called a delta volume, changelog, or save location.
How does that work?
Okay, so when a write comes to the source for the first time after the session starts, the original data at that address is copied to that predefined save location.
So the history goes to the save location.
Right. Then, the pointer in the target is updated to point to this data in the save location. After that, the new write is updated on the source.
And if you write to the target...
If a write hits the target, the data is copied from the source to the save location, and then the new write is updated on the save location. Again, preserving the original before the target's view changes. Crucially, subsequent writes to the same data block on the source or target do not trigger a copy operation to the save location. The original is already safe.
So the save location just holds, it changes the delta, and the target is basically a map pointing to either the original source data or the changed data in the save location.
Exactly. That's the elegant part. When you read from the target, it's a combined view. Unchanged data blocks, since the session activation, are read directly from the source, while data blocks that have changed are read from the save location.
So the target gives you that consistent point-in-time view.
Precisely. But there's a significant constraint. Unavailability of the source device invalidates the data on the target, because the target relies on the source for all the unchanged blocks.
Okay, that's important. But the storage saving must be huge.
Massive. The target volume itself contains only pointers, so the physical capacity required for the target is a fraction of the source device. The actual capacity required for the save location depends entirely on the amount of the expected data change, not the full source size. This is where you get major cost savings.
That's the real power for efficiency. Now, once you have these replicas and things change on both source and maybe the target, how do you sync them up again efficiently? Copying everything back seems crazy.
You absolutely can. It would be a performance nightmare. This is the challenge incremental resynchronization and restore operations solve.
How do they figure out only what's changed?
Very efficiently using bitmaps. Remember the bitmap from FS snapshots? Smaller idea here.
Okay.
Think of a bitmap where each bit represents a specific data block, maybe 32 KB. When the replica is created, the bits in the source and target bitmaps are all set to 0, meaning identical at that point.
Got it. All zeros.
Then, as changes happen, any changes to the source or replica are flagged by setting the appropriate bits to 1 in the bitmap. It creates a precise log, block by block, of what changed where.
Like a change tracker.
Exactly.
Right.
So when resynchronization or restore is required, a logical OR operation between the source bitmap and the target bitmap is performed.
A logical OR. Okay, what does that tell you?
The resulting bitmap highlights all blocks that have been modified on either the source or the replica since the snapshot. This enables an optimized resynchronization or a restore operation because it eliminates the need to copy all the blocks.
So you only copy the blocks where the OR result is 1.
Precisely. Only the specifically changed blocks are transferred, saves massive amounts of time, bandwidth, and storage I/O, but there is a critical choice.
Which is?
In either case, changes to both the source and the target cannot be simultaneously preserved. You have to decide. Either the replica updates to match the source, resync, or the source reverts to match the replica, restore. You pick which version wins.
Can't have it both ways. Makes sense. Any other main categories?
Just briefly, there's also network-based replication. Here, the replication smarts aren't on the host or the array. They're on a dedicated network device or appliance between the hosts and storage.
Like a middleman managing the copies.
Kind of, yeah. It intercepts and manages the data I/O. The main benefit is it combines the benefits of array-based and host-based replications by offloading work from both. It's often ideal for highly heterogeneous environments, lots of different servers, different storage vendors.
Ah, so it provides consistency across different gear.
Exactly. It acts as a universal replication engine. A good example is continuous data protection, CDP, which offers super granular recovery points, often using this network approach for local and remote replication, often chosen for flexibility or specific RPO needs. 3. Restoration and restart, getting back online fast.
Okay, so we have these amazing replicas built with all this clever tech, ensuring consistency, efficiency, fantastic. But what's the end game? How do we actually use them to get systems back up after something goes wrong? It's
Yeah.
all about getting back online fast.
Absolutely. That's the whole point. Minimize downtime and data loss. It really boils down to two main scenarios for using the replica, driven by the business's RTO and the specific problem.
Okay, two scenarios. What are they?
The first is restore. The goal here is simple. Copy data back from the replica to the source if the original data is lost, corrupted, or just needs reverting to a known good state.
So fixing the original using the good copy.
Right. The replica acts as the authoritative, healthy copy, overwriting the problematic data on the original source volume. And thanks to those bitmaps we mentioned, it's often incremental, only copying what's needed.
When would you use restore?
Typically for logical corruption, bad data inside an application, or accidental deletions, or maybe reverting from a bad software update, it's about bringing the original system back to health.
Okay, the digital undo button. What's the second scenario?
The second is restart. This is for when you need to immediately get business operations back online using the replica itself, without taking the time to copy data back to the original source.
Whoa, so just switch over and run on the replica.
Exactly. This is for situations where downtime must be absolutely minimized, sometimes down to seconds. The replica volume is simply brought online and configured to serve as the new primary data source. It's crucial for apps with extremely low RTOs.
So if restore is like copying files back to your C drive to fix it, restart is like unplugging the broken C drive and just booting directly from the D drive, your replica, immediately.
That's a perfect analogy. Restart is about that near instantaneous cutover to resume operations, minimizing downtime to seconds or minutes. It's the ultimate business continuity play for mission-critical applications where any outage is unacceptable.
Like financial trading, emergency services, things that just can't stop.
Precisely. They can't afford minutes, let alone hours. They need to fail over almost instantly, and that's what a well-designed restart strategy using local replicas allows. IV, local replication in virtualized environments. The VM angle?
This is where it gets really interesting for so many of our listeners, I think, because virtual machines, well, they're everywhere now, aren't they? How does all this local replication magic apply to virtualized environments? Does it add complexity or maybe simplify things?
You're hitting on a key point. In a virtualized world, protecting your virtual machine, your VM data, and that includes the whole OS, the apps, the config, everything, it's absolutely imperative. Losing a VM is like losing a whole server, maybe worse if you have many on one host.
Yeah, the impact is multiplied.
Right. And yes, virtualization often simplifies management, but it definitely introduces new things to consider for data protection, especially around how you back up and replicate VMs to keep everything working.
So let's start with backups. How do you protect VMs effectively?
Well, the crucial importance of VM backup and optimization can't be overstated. Just like physical servers, VMs can suffer data loss or corruption. Losing a VM means losing the OS, app, data, everything. So backing them up is non-negotiable.
But with potentially hundreds or thousands of VMs, that sounds like a ton of data to back up. How do you make that efficient?
Absolutely. And this is where optimization with deduplication really shines for virtual environments.
Deduplication, finding the identical bits of data.
Exactly. The dupe techniques significantly reduce the amount of data you need to store and transfer for VM backups. Its effectiveness is really clear when you have VMs with similar configurations.
Ah, like lots of VMs running the same Windows version or the same Linux.
Precisely. Think how many VMs might run the same OS or similar versions of applications. There's a huge amount of redundant data, identical OS files, app executables, libraries. Dedupe identifies and eliminates that redundancy.
Saving storage and network bandwidth.
Massively. Saves huge amounts of storage on your backup target and cuts down network traffic during backups. And the same dedupe methods, source-based, target-based, inline, post-process, apply here, just like in physical environments.
Okay, so dedupe helps with backups. What about replicating VMs themselves? I know about VM snapshots.
Yeah.
How to fit in.
Right, the VM snapshot. This operates directly at the hypervisor level. That's the software like VMware, ESX, or Microsoft Hyper-V managing the VMs. It takes a snapshot of the VM, capturing its complete state at a moment in time.
And what does it capture? Just the disk.
More than that. It captures the VM's dynamic state BIOS settings, network config, even its power state, on, off, suspended. And crucially, all the VM data, including all the files that make up the VM, like its virtual disks, the files acting as hard drives, and even its memory RAM content.
Wow, memory too. So it's like freezing a running computer completely.
Exactly. Like pressing pause on a running system and saving that exact state. And similar to the FS snapshots we discussed, a VM snapshot doesn't copy the entire virtual disk right away. It uses a separate Delta file to record all the changes to the virtual disk since the snapshot session is activated.
Ah, the copy on first write principle again, but at the VM level.
Pretty much, yeah. Very space efficient for recent changes. The main use case. When a VM needs to be reverted to the previous state in the event of logical corruptions, bad software update inside the VM, accidental file deletion, you can revert the entire VM back to that known good snapshot state almost instantly.
That's powerful for fixing mistakes. But there's a catch, right? What happens when you revert?
Important caveat, yes. Reverting a VM to a previous state causes all settings configured in the guest OS to be reverted to that PIT when that snapshot was created. It's a full rollback. Any changes made inside that VM after the snapshot was taken are lost.
Okay, good for quick recovery, but you lose recent work. Are there other limitations to these hypervisor snapshots?
You're right to ask. While super useful, they have a couple of key challenges. First, they do not support data replication if a virtual machine accesses the data by using raw disks.
Raw disks,
Yeah.
like directly accessing storage, bypassing the hypervisor's files.
Exactly. If a VM uses raw device mapping, RDM, or similar to talk directly to a storage LUN, the hypervisor snapshot can't capture that raw data. You'd need array-based replication for that specific LUN.
Okay. And the other challenge?
Performance. Using the hypervisor to perform snapshots increases the load on the compute and impacts the compute performance. The hypervisor is doing the work managing the deltas in I/O, consuming CPU and memory.
Which can slow down other VMs on the same host.
Potentially, yes, especially in busy environments. It's generally recommended not to keep VM snapshots around for very long because of this overhead. They're great for short-term recovery points.
You mentioned VM clone earlier. How does that differ from a snapshot? Are they related?
They're related because they both involve duplicating a VM, but they serve different purposes. It's a key distinction. A snapshot captures a point-in-time state with a Delta file, dependent on the original VM.
Yeah.
A VM clone, however, creates a complete independent duplicate.
Fully separate.
Fully separate. When you clone, you create a whole new self-contained set of VM files, virtual disks, config files, often memory state. It's a full copy with no ongoing connection to the original.
So what are clones used for then?
Often for things like rapid deployment, quickly rolling out identical VMs from a template, great for testing and development, providing fully isolated copies for devs or testers, or just creating a new server instance quickly.
And the key difference from a snapshot is that independence.
Exactly. A snapshot depends on the original. Delete the original, the snapshot is useless. A clone is fully independent. Deleting a snapshot changes the original VM, merges the delta. Deleting a clone doesn't affect the original at all. Think snapshot, temporary bookmark, clone, brand new, identical book.
Okay, that clarifies it.
Yeah.
Now, besides hypervisor snapshots, can we use those array-based methods we talked about for VMs too?
Absolutely. And this is a powerful alternative. Array-based local replication for virtual machines. Instead of relying solely on the hypervisor, local replication of VMs can also be performed at the storage level using array-based local replication, similar to the physical environment.
So the storage array handles replicating the VM's virtual disk files, just like any other data.
Precisely. From the array's perspective, A VM's virtual disk, like a VMDK or VHDX file, is just another set of beta blocks on a LUN it manages. It doesn't really care it's a VM, it just replicates the underlying storage volume.
And the big advantage there is offloading the work from the hypervisor.
Exactly. It offloads the replication burden from the hypervisor, freeing up its CPU and memory to just focus on running VMs. The array's dedicated hardware handles the data copying efficiently.
So better performance, less impact on the VMs themselves.
Right. This is crucial for high-performance virtualized environments, especially those running big databases or demanding apps inside VMs. It also allows for very consistent snapshots across multiple VMs if they live on the same replicated LUN. You might choose this for large-scale, tight RTOs or when hypervisor performance is paramount.
That's a fantastic overview. Now, to really cement this, let's walk through that practical example from the sources. A manufacturing organization with a critical database. How would we design a replication solution for them using these concepts?
Excellent idea. It really shows how these concepts translate into real-world, cost-effective designs. Let's lay out the scenario for you.
Okay.
We have this manufacturing org. They have a mission-critical database. It uses 1 TB of storage, currently on a high-end array with RAID 1 for availability.
Okay, boring stuff.
And they need 24/7 availability. They estimate about 60 gigabytes of data changes in a typical 24-hour period. So always on, steady changes.
What are their specific protection requirements? Must be pretty strict for mission-critical manufacturing.
Indeed. Stakes are high. They have a few key needs. First, a solution for logical corruption. If the data inside the database gets messed up, they need to recover cleanly. Second, a maximum recovery point objective, RPO, of 1 hour.
Wow, only 1 hour of data loss max. That's tight.
Very tight. Drives how often replicas are made. Third, they need to be able to restore up to 8 hours old data, giving them a decent window to go back in time. And finally, the classic requirement. Minimize the storage used for data protection. Cost is always a factor.
Okay. Logical corruption protection, 1 hour RPO, 8-hour restore window, and minimal storage use. That's a balancing act. What's the recommended solution?
The recommended solution based on these needs is pointer-based virtual replication technology, specifically that copy on first write to a save location method we discussed.
Ah, the space-efficient array method. Why that one specifically?
It hits all their requirements perfectly. It allows them to minimize storage while providing those granular point-in-time copies needed for logical corruption recovery, and it can easily meet the 1 hour RPO and 8-hour restore window.
How would full mirroring compare here?
Full mirroring would be far too expensive storage-wise. It would need another full 1 TB just for the replica's 100% overhead. COFA would also eventually use that 100%. This pointer-based virtual approach lets them meet their goals without doubling their storage cost.
Makes sense. How do they implement it to meet the 1 hour RPO and 8-hour window?
Using rolling replicas. The strategy is to create pointer-based virtual replicas every hour.
Every hour, okay.
And they'll maintain a total of 8 such replicas, 1 for each hour in that 8-hour recovery window. As the 9th hour arrives, the oldest replica from hour 1 is basically refreshed or replaced by the new one.
So they always have 8-hourly recovery points available covering the last 8 hours. Clever.
Exactly. Gives them great flexibility.
Now, for the aha moment, the storage calculation, how does this truly minimize storage? This is where the rubber meets the road, right?
Absolutely. This is where the power of this tech becomes crystal clear. We know they average 60 gigabytes of data changes in 24 hours. That works out to 60 gigabyte, 24 hours equals 2.5 gigabytes of data changes per hour on average.
Right.
Now, the source material indicates that on average, 20 gigabytes of data changes every 8 hours. Thus, each replica would require 20 gigabytes. This means over the 8-hour retention period for any given replica, about 20 gigabytes of new, unique changed data accumulates in the save location that it points to.
So each hourly snapshot effectively tracks about 20 gigabytes of unique changes over its 8-hour life.
That's the idea for calculating the total space needed. Since they're keeping 8 distinct replicas active for that 8-hour window, each contributing to or pointing to that pool of changes, the total physical storage required for the save location across all 8 replicas is approximately 160 gigabytes of physical storage.
Wait, 116 gigabytes?
Yep. 8 replicas times roughly 20 gigabytes of unique changes each accounts for.
So for a 1 terabyte original database with 60 gigabyte of changing daily, the total storage needed for all those hourly 8-hour retainable replicas is only around 160 gigabytes?
That's right.
Wow. That's a massive reduction compared to the 1 TB a full mirror would need. Like 85% savings on protection storage. What does that mean for the company?
Exactly. That is the massive impact. It's a huge financial and operational win. That 160 gigabyte requirement versus the 1 TB source size, it's achieved precisely because of pointer-based virtual replication only storing the changes. For the manufacturing org, it means they meet incredibly strict RPO store needs without breaking the IT budget.
Frees up money, makes growth easier.
Right. Provides a level of data protection and continuity that might otherwise be prohibitively expensive. It really shows the power of intelligent data management design.
V. Wrapping up. Why this knowledge matters to you.
So let's wrap this up. What does all this mean for you, our listeners? Whether you're actually planning IT infrastructure, running a small business, or maybe just curious about how your digital life is safeguarded. Well, it means that the seemingly simple act of copying data is actually a highly sophisticated, deeply engineered process. It fundamentally underpins the reliability, the performance, really the very existence of nearly every digital service you use.
It's everywhere.
Understanding local replication highlights the clever engineering that lets businesses run 24/7, giving us immediate access to information and providing that crucial invisible safety net against things going wrong. It's the silent hero of the digital age.
Yeah, from the humble snapshot on your laptop's backup, all the way up to complex array systems protecting petabytes for global companies. Those core principles, speed, consistency, efficient resource use, they're paramount everywhere. It's the plumbing that keeps our digital world flowing.
And it also shows us there's always a calculated trade-off, isn't there? It's a careful balance between the cost of the solution, the performance you get, how much data loss you can tolerate, your RPO, and how quickly you need to get back online, your RTO. Choosing the right replication strategy is a careful calculation, driven by real business needs, often leveraging virtualization for incredible efficiency, like we saw in that manufacturing example. It's not just IT stuff, it's core business strategy.
We've certainly journeyed through the ins and outs today. Local replication as a tool for backup, fast recovery, testing, even decision-making. We've explored host-based, storage-based solutions, the ingenious mechanics, and how it all applies in the VM world.
Indeed. We've seen how concepts like dependent rights ensure integrity, how pointer-based tech slashes storage needs. It really is a sophisticated dance of data ensuring availability and resilience while saving resources.
So looking ahead, as our digital footprint just keeps expanding exponentially, and the lines between physical, virtual, cloud, they keep blurring. How will these local replication strategies evolve? What's next? What new efficiencies, maybe entirely new methods will emerge to keep our data not just accessible, but perpetually available, perfectly consistent no matter what? Will AI play a bigger role? What about containers, edge computing? Does that change the game again?
That raises a really important question, doesn't it? One for all of us to consider as we navigate this constantly shifting digital landscape. It certainly promises continued innovation in how we protect our data.
And that's our deep dive for today. Thank you so much for joining us on this exploration of local replication. Until next time, keep digging for those insights and stay well informed.